Hi everyone. So, I just wanted to start off by showing you these questions again. All of these are the Chapter 11 exercises, and these are the questions which you should be completing. Okay, and as I said, trapezium rule. I'm not doing that with you, so you need to ask the other teacher. Okay, so if you need to write these down or whatever, pause the video. Otherwise, I'm going to carry on with Chapter 11H. So, as you can see here from 11H, it's finding areas. Now, this topic, you've done it many times in the past. Okay? Now, hopefully you should already know that when you integrate a function, let's say the function y equals fx. Okay? So let's say if you was to plot y equals fx, let's say if you just came out with something like that. Okay? So if you integrate y with respect to x. Okay, so if you integrate this with respect to x, it finds the area between your curve and the x-axis. Okay, so if you integrate your function with respect to x, it finds the area between the graph and the x-axis. Okay, so it'll find that area there. Okay, however, remember limits. Let's say if you had the limits b and a, it would find the area between those two x values. Okay, so you've done it many times in the past, and yeah, I expect you to know that. Now, it's the same idea with this stuff. Okay, it's literally the same, it's just harder integration. Okay, so let me just get rid of that. Yeah, you're using that same idea. So the diagram shows part of the curve y equals 9 over the square root of 4 plus 3x. The region R, so it's already labelled, is bounded by the curve, the x-axis. So the x-axis, the lines 0 and 4, as shown in the diagram. Use integration to find the area of R. So the area, as I've literally just said, is the integral of your function. And because we're trying to find the area between the curve and the x-axis, we integrate with respect to x. Okay, now we've gone in between the curve and the x-axis. By doing the integration, we need to now put the limits in of 4 and 0. Okay, so this is something you'd have just done in year 12. However, now is when the year 13 stuff comes in, the actual integration of it. Now, the bottom of this fraction, it's a square root, isn't it? So you could write it as 4 plus 3x to the power of a half with 9 on the top. Okay. Oh, I've put double brackets there. Let me just get rid of that one. Okay, so if we didn't have the power of a half here, let's say if it was just that, this would be a natural log. Okay, when you integrate this, it would be a natural log. However, if you have a power across the entirety of the bottom, what you can do is write it as a negative power and then just integrate normally using reverse chain rule. Okay, so because we have a power across the entirety of the bottom of this fraction, so here we've got a power across the entirety of the bottom, we can just write it as a negative power. Okay, so I'll say that once more because this is one of the important things that you need to spot when you're doing these questions. So if you have a fraction where the bottom of the fraction, the denominator, has a power across the whole thing, you write it as a negative power. If you don't have a power, let's say that instead, that integrated would be natural log. Okay, whereas this one, you write it as a negative power. Okay, so power across the entire bottom, you write it as negative power. If you don't have a power, don't write it as -1. because if you increase it by 1, 0, divide by 0, you can't do it. Okay, so it has to be a natural log. So let's finish this question. So 9 is a constant, isn't it? So we could pull it out. Now, reverse chain rule. Give me a sec, let me just write all my limits in. Reverse chain rule. So imagine if the inside of this bracket was just x. If this was just x, we increase the power by 1, don't we? Then divide by the new power. So let's just stick the 9 back at the front. So increase the power by 1, a half. Divide by a half, you get 2. Okay? Now, the inside of the bracket stay the same. We've increased the power by 1, so a half. And now we divide by the differential of the things inside the brackets, because it's not just x, is it? The differential of the inside of the brackets is 3. So we need to divide that by 3. What's the best way of doing this? Let's just put 2/3 there. Okay? So increase the power by 1, divide by the new power, and divide by the differential because it's not just x. Okay, reverse chain rule. Now, I need more space, so I'm going to get rid of all of this. Okie dokie. So, now finishing this off. We've got 9 lots of. Now we need to sub these values in, don't we? So we've got 2/3 of 4 plus 3 lots of 4, all to the power of a half, minus, if you stick 0 into this, so 2/3 lots of 4 plus 0 to the power of a half. Now, if we continue with this, we've got 9 lots of, so 4 plus 12 is 16. 16 to the power of a half is 4. So 4 times this is 8/3. 4 plus 0 is 4. To the power of a half is 2. So minus 4/3. So we've got 9 lots of 4/3, which is 9 times 9 divided by the 3 is 3. So overall 12. Okay. So as I said, no more difficult. The only bit that's the only bit that's new is the actual integration bit in the middle. Okay, and for this integration you could be asked to use partial fractions, you could be asked to use substitution, by parts, reverse chain rule like this one. You could be asked any sort of integration method. Okay, and there's the nicer written version. Okie dokie. So, a few lessons ago I spoke about the things on this slide. Okay, so if you have two curves, let's say the first one is called y equals fx, and the second one is called y equals gx. Okay, now if we wanted to find the area between these two curves, so let's say if fx is the top one, gx is the bottom one, you can find the area between fx and the x-axis. So find this big area. So find this massive area here, and then you can take away the area between gx and the x-axis to find the shaded area up there. Okay, so to find the shaded area, you can find the area between fx and the x-axis, find the area between gx and the x-axis, then take them away. Okay, and that's what this formula here summarizes. Okay, so find the area below the fx, find the area below gx and take them away. Then this formula here is just a simplified version using some laws of integration. Okay, because they have the same limits and because they're integrating with respect to the same letter, you can actually combine them to create a single integration. So this you can use for the majority of the time. However, you need to make sure that you do in the top curve take away the bottom curve. Okay, so an example. The diagram shows part of the curves y equals sine of 2x and y equals sine x cos squared x, where x is between 0 and pi over 2. Find the area R. So the area. So, as I've said, we're integrating between the 2 points here, so 0 and pi over 2. The top curve, so as I've said, you need to ensure that you're doing the top curve minus the bottom curve. The top curve is sine of 2x. The bottom curve is sine x cos squared x, and that's all integrated with respect to dx. Now, this integration doesn't look very nice, okay? Remember, there's many ways of integrating that you now know. So, if you was to look at these individually, sine of 2x, well, it's a double angle formulae, isn't it? You could use the double angle formulae. However, you could just integrate it straight away, couldn't you, using reverse chain rule? If you was to integrate that using reverse chain rule, so imagine if this was just x instead of 2x, sine of x integrated is minus cos of x. Yeah, if you integrate sine, it changes sign. But because this isn't just x on the inside, it's 2x, you need to divide by the differential of the inside of the brackets. Okay, obviously I don't have brackets drawn, but you know what I mean. Okay, so this integrated is this. So now just this second integral. So sine of x cos squared x. Now I prefer the squared to be separate. Now this, the outside of the bracket, if you pay attention, is the differential of the inside, isn't it? Yeah, this is where it becomes very difficult in integration, because you need to be able to spot these things. The outside is the differential of the inside. Okay, so because we have the differential on the outside, we can try and use reverse chain rule. So leave the thing on the outside and now try and just integrate this using reverse chain rule, this cos x squared. So imagine if this was just x squared integrated, so you increase the power by 1, so it becomes a 3. You divide by that new power. However, because this isn't just x, it's cos x, you need to divide by its differential. Now cos x differentiated is minus sine x. Okay, now sine x and sine x cancel, which makes it perfectly fine to do this. Okay, if we didn't have this sine x to cancel with this sine x, we could be dividing by 0, couldn't we? Yeah, sine of x can be 0, can't it? So we couldn't divide if we wasn't able to cancel these out. Okay, and now a minus and a minus make a plus. Okay, so our integral actually becomes minus cos 2x all over 2 plus cos x cubed all over 3. Now subbing in our limits, subbing in pi over 2 first, so cos of pi over 2 times 2, so cos of pi is minus 1, that's over 2. Then this second one, so cos of pi over 2 is 0, isn't it? So all of this would just be 0. Then we take away when you sub 0 in, so 0 into this, cos of 0 is 1. And again, cos of 0 is 1, so a third. Okay, yep, that's all done. Now, minus a half, so that becomes a half, plus a half, minus a third. Okay, so 1 take away a third is 2/3. Okay, so that's that one done. I don't think there would be any questions with that one. I don't think, to be honest. The only bit that's difficult is this bit. Okay, when you're actually spotting how to integrate, and that will just come with practice. You're going to need to do a lot of questions to be able to do this sort of thing. Okay, so carrying on. There's a nicer version of the answer written. I mean, it's got lots of it missing, but you get the point. Okay, so there's one for you to try yourself. Okay, I want to go through this afterwards in a minute, just to make sure you know what you're doing and just to give you another example. But pause the video here, have a go at this one yourself, and I'll go through it in a moment once you unpause. Okay, so this is a relatively simple one. Area. You need to integrate your function, so 3 over the square root of 1 plus 4x with respect to x between 2 and 0. So again, we can rewrite this bottom as a power, can't we? Bottom of this, because it's all in a square root, you can write it as power of a half. And now here, as I was saying earlier, you have a power across the entire denominator. When you have a power across the entire denominator, you can write it as a negative power. I don't know why I wrote a 4. Okay. So, now we've got that. This 3, I like to bring them out, as I've said many, many times. And now that is just reverse chain rule again, isn't it? You can increase the power by 1, divide by the new power. So increase the power by 1, you get 3 over 2. Divide by 3 over 2, you get 2/3. I don't know why I've written 4 again. It's starting to annoy me now. So 1 plus 4x, and we've said that the power was 3 over 2. But because the inside isn't just x, we need to divide by its differential. So divide it by 4. And now we're trying to get that between 2 and 0. I'm going to tidy it up slightly just so it's easier to work out. So if you was to times this 3 on the inside, now you can do that because it's just a constant, it's not going to really affect it much. So 3 times the 3 cancels. 2 times this 4th, so you're just going to end up with a half of 1 plus 4x to the power of 3 over 2 between 0 and 2. Now I'm going to double check that. 3 times the 3rd, so those 2 cancel. The 2 and the 4, that 2 will cancel with this 4 to leave you with 2. Okay, now subbing those values in, so 2 into there, so a half times by, so 1 plus 4 times 2 is 9. And then the second one, when you sub 0 in there, so it's going to be a half, lots of 1 to the power of 3 over 2. So a half times 9 square rooted is 3, cubed is 27. Then this is just going to be a half still. And now 27 halves, take away 1 half, is 26 halves, or just 13. Okay? So, that's it for 11H. I'd like you to now go ahead and just have a go at the questions in the exercise. And yeah, I've put them on to show my homework so you can see them. Yeah, see you in a future lesson.